You heard it already, I've been hopping around quite a while in my life. I never planned this. I always wanted to stay in that little village that I came from. But life is a river and you have to float on it. And science is a very nice float and it can take you anywhere in the world. And what I'm doing today is, because this is more a science communication lecture, I will pretty much teach you English and I tell you my life's story rather than so much about the science. The overarching topic of my research career has been photochemistry, so activating chemicals with the help of light so that they do something, for example, a chemical reaction. And we have done that on laboratory scales as well as on larger scales outdoor, and more recently, you heard that already, we went small and we started microphotochemistry. And that's also a reason why I know Liu Sensei. This picture here is not a picture of the current flooding that's occurring in Queensland. This is only 3 hours away from where I come from. This is the Whitsunday Islands, so it's a very nice holiday location, and it's definitely better than Cairns because it has less Japanese tourists swimming around. Have you ever asked your supervisor why he or she became a chemist and why he or she is doing what he is currently doing in terms of research? I ask usually every student why he chose to study chemistry. And I will tell you the same thing. So I was infected with organic chemistry when I was a seventh grade student in secondary school in Germany. By then I was a very ordinary student, rather bad than good, and suddenly we started in our chemistry lectures these models, these so-called ball and stick models. And suddenly chemistry became very colorful and very three-dimensional. And that fascinated me, and that actually sparked me. The models became more complicated. A few more colors came in, for example, red. Suddenly things like chirality appeared, that molecules are described like hands, and I thought that is very great. So when I was 13 years old, I decided that I want to be an organic chemist. Until that day, I wanted to be a general, and some of my students actually tell me that I actually talk like a general still. Okay, so I was 13 years old and I knew what I wanted to do. Then when I went to university, of course, chemistry became very complicated, it became very broad. And when I was like an M1 student, at least nowadays, I did a photochemical reaction as part of my undergraduate degree. And this is the photochemical reaction that I started. And it really enlightened me. And from that day on, I not only wanted to be an organic chemist, I actually wanted to be an organic photochemist. And it's a cycloaddition reaction between a compound known as an azarine. You can ring open it here with the help of a sensitizer, and then it hops onto this alkene and forms a 5-membered ring. And that is how it works. So just very briefly, it involves an electron transfer, so an hopping of an electron between this DCN, which is the catalyst. You are creating such a radical cation, and this radical cation now jumps onto the alkene and forms eventually the 5-membered ring. And what was really fascinating was the way it was done. I didn't use any oil bars or any reflux condensers. I used a magic black box. And that magic black box had a name. It was known as a Ryonet reactor. There was no heating inside. There were only a few lamps inside. I put a test tube. It was a very simple thing to do. A test tube just into this chamber, into this opening there. And after a couple of hours, suddenly had a very complicated product. The dark control, which was done at the same time, by just wrapping one of the samples with tinfoil, had no reaction at all. So it was light that actually caused this reaction to happen. When you look a little bit at the stereochemistry, you have 2 chiral centers here. And under these conditions, these 2 chiral centers are pretty much anywhere. So you do not have any stereoselectivity. And that is also surprising because without the help of this DCN, the reaction also occurs, but you get quite high stereoselectivity. And these 2 groups here are mainly trans towards each other. So that was something very cool. With a flick of a switch, I was able to make complicated molecules. that I couldn't do in any other mean. And that thing, this fascination, is still, if you like, lasting to this one day. So what is organic photochemistry? I just want to give you a very brief introduction. When you ask the IUPAC, you get a very simple definition. Photochemistry is a branch of chemistry concerned with the chemical effects of light. That's one of the most easiest definitions when you check the IUPAC. Okay? And what we are talking about is typically we have a substrate that is in a ground state, then we hit it or we load it with some energy, which is a photon. We create a higher energy state that we call an excited state, and that excited state now has a number of options, and one of the options that we are interested in, of course most, is they form products. There's a catalytic version of that. It's not called photocatalysis. It's known as sensitization. So here the light is taken on by a sensitizer. The sensitizer reaches an excited state and then transfers this energy, like in a car accident, onto the substrate. And you can also get a product very, very nicely. These are just two of the many, many different types of photochemical reactions that are out there. But the main point is you're adding energy with the help of light. And when you look like this is h nu, what we typically write onto an equation, and h nu is nothing else but the amount of energy that you put in there. And typically, we are not talking with a frequency, we're talking with the wavelengths. So we can choose the amount of energy that we put into a molecule by simply selecting the proper wavelengths. And if you just look at typical ranges, we work as photochemists between 200 and 700 nanometer. That corresponds to 600 to 170 kilojoules per mole. And when you compare that to typical bond dissociation energies, you can obviously do a lot of things with that. You can change a lot of bonds using these amounts of energy. And what is really interesting is, photochemically, you can make very strange molecules very easily. Why is that so? Now let's look at a chemical reaction in the ground state that is thermally not allowed because it's thermodynamically not favored. You have a ground state substrate here, and here's a product, a very exotic one. It's higher in energy. So obviously, you have here an endothermic reaction, so it's not going to happen. But with the help of light now, I can catapult my substrate to a higher energy state, and suddenly, if you follow the energy path now, you have an exothermic reaction. So we are investing some energy in order to make something very strange happening. And that is a very simple thing to do. And here are just a few types of photochemical reactions. You have all these radical substitutions that you know from your lectures. They are photoredox reactions, isomerizations, a very typical photochemical reaction, and a few more. Often they come with high selectivity, and what is really interesting is, in terms of the way you're doing it, you do it with a flick of a switch. You turn a light source on, a reaction proceeds. You turn it off, the reaction stops. You cannot do that very easily with thermal reaction that way. Okay? However, when you ask the industry doesn't know very much about photochemistry. They're actually very scared. And there are a lot of stereotypes out there that are very common when you talk to industry people as a photochemist. And one is the small scales and the high dilutions that you typically work on, the low yields that are very commonly accounted for, the exotic equipment, high cost, high energy demand, high cooling water demand, etc., etc. These are all stereotypes, and they go back a little bit to maybe 30, 40 years ago when photochemistry was really a young discipline still. On the other hand, when you look at common research practice, how is research done in industry, and I know because I worked for a couple of years for Bayer, you typically work on smaller than 100 milligram scales. So this argument of low yields is not really valid. In vivo screening, you need 100 milligrams, but even that you can achieve photochemically quite easily. In terms of development of a drug or a new agrochemical, typically 75% of all compounds that are synthesized fail sooner or later anyway. So as a research tool, why not trying photochemistry? And what I experienced a lot while I was working for Bayer is that photochemistry was actually seen as a scare. And whenever the SciFinder database or so gave as the only way of making a target molecule, a photochemical reaction, it wasn't even tried. It was immediately abandoned. And as agrochemists, of course, we worked a lot in greenhouses and later on outdoors. Photodecomposition was very often blamed when a molecule didn't perform outdoors in sunlight as it did indoors in a greenhouse. So obviously there are a lot of problems here with the acceptance of photochemistry, with the reputation of photochemistry, and also the knowledge of photochemistry. I assume that you don't do any photochemical reaction during your degree. You may actually get some photochemical knowledge in some of the lectures when it comes to radical substitution reactions, etc. But I can tell you that photochemistry is not so bizarre as a lot of people think. And this leads me to my early years doing my master project. That was 1995. I joined the same group that I did my project for, and I was very delighted to do that. It was a very nice group. And I investigated this reaction here, photoacylation of quinones, with the help of some very common photochemical equipment. And the reaction is shown here. You have a quinone, which you can buy. You have an aldehyde that you can also buy in large quantities, very cheap. And with the help of light, you do an acylation reaction. So here is the aldehyde, and the hydrogen went up there to that oxygen. And this reaction has a number of interesting facts. The first thing is it's very old. It was discovered by accident more than 100 years ago in Germany by a German fellow who really accidentally discovered this reaction. And when you look at the procedures from those days, and fortunately as a German I'm able to read all this, he just exposed mixtures on the roof of his institute for a number of months, in closed vials, and then brought them back in and analyzed them. Very interesting to read. When you look at the reaction itself, it has a perfect atom economy. You're not wasting any atoms here. All the atoms from the starting materials appear in the product. And that is a concept now known in green chemistry. How efficiently are you using your atoms? There's no hydrochloric acid formed here, there's no water formed, nothing. Only one product. The yields are quite good, at least for a number of R groups, and we summarized the 110 years of this chemistry a couple of years ago, and it was a really interesting thing to write this article. And the other good thing was we wanted to do this reaction outdoor, and I'll show you later on how we did that. So the quinones absorbed already in the visible spectrum. They usually have a pale color if they are not substituted, and that means they absorb invisible light, and you can take advantage of that. The mechanism is fairly easy. It's the light goes into the quinone. The quinone then is able to remove a hydrogen atom from the aldehyde. You're generating this radical pair here, either in cage, they may separate, but they may also form directly then the carbon-carbon bond. You have then a tautomerization to get the aromatic ring back, and you have your final product. It's as simple as that. It's also a very nice alternative. The structure here can be made in many other ways, but ours was short and started with commercially available materials, whereas the classical Lewis acid Friedel-Crafts reaction required to introduce protecting groups, and also the freeze rearrangement required, first of all, the synthesis of this monoester, and also a protection group down here, which had to be removed after the rearrangement. And last but not least, these are very interesting starting points for a number of biologically active compounds. And here's just a summary of molecules that have been synthesized from precursors that have this structural element inside. So obviously it's a very useful reaction. So what I did is then I started, Josh, I said, let's go. And I just grabbed a number of aldehydes that were in the laboratory, just put them together in this immersion well reactor, and then irradiated them in benzene or acetonitrile. Yields were okay to quite good. They were never really optimized, and we published that in a number of papers later on. What was funny is that even an old reaction like this still has a number of surprises.